In this video, we will explore Thevenins theorem. Thevenins theorem is one of the most important theorems in circuit analysis. And in this part, we will focus on the principles behind the theorem and give some examples. So what is Thevenins theorem? So let's say we have a linear two-terminal circuit, and we know that a linear circuit means that it has to satisfy two properties, and that is the additivity property and the homogeneity property. And out of that two or linear circuit, there are two terminals. Let's designate that as terminals A and B. And let's say that from those terminals, another circuit, or sometimes we call it a load, is connected to those terminals. According to Thevenins theorem, this linear two-terminal circuit can be replaced by a simple circuit consisting of a voltage source that is in series with a resistance that looks like this. So what we did is this part here is replaced by this part here. So let's have another real circuit. So let's say we have this circuit, and if we consider this part here to be the linear two-terminal circuit, that part can be replaced by a simple circuit consisting of a voltage in parallel with a resistance that looks like this. So this part here uh, is replaced by this part. So this part here is the one that is connected to this part. So actually this part here is this one, and we leave that as it is. Uh, this is the part that we want to replace by this circuit here. So the converted part of the circuit is what we call the Thevenins equivalent. So the one that we identified as a linear two-terminal circuit, and then replaced by a voltage in series with the resistance. So Thevenins theorem, just like superposition, breaks up a complicated circuit problem into pieces of smaller problems. Now the challenge here is finding what is that voltage that is in series with the resistance. So how do we find the VTH? We've already identified the part of the circuit that we need to convert to Thevenins equivalent, and that part is this one. And once that is converted, we can then use this modified circuit to solve the problem. So how do we get VTH? So we need to remove the rest of the circuit that is connected to that part that we've converted, or that needs to be converted. So that part here is this one. So we remove that one, and that becomes like that. And from there, we compute for the voltage across the open terminals. So this is the open terminals. And let's call that voltage V sub OC, where the positive uh, side is the side where terminal A is located. It's because our voltage VTH, the positive uh, terminal, is facing the terminal A on the modified circuit. Okay, so once we get that voltage VOC, that voltage then becomes our uh, voltage VTH. After getting VTH, we also need to find RTH. And to do that, again, we go back to the circuit that we want to convert. The rest of the circuit detach. And we disable all independent sources. So here we have an independent current source. We need to remove this one. So removing a current source means that we isolate it. So we disconnect it from the circuit. And effectively, that means that this will now be our uh, a new circuit where there are no independent sources. And then after that, we compute for the resistance across or looking through the open terminals. We call that a resistance looking through the open terminals. And that resistance becomes our RTH. Okay. Now, that part of getting RTH, we call that the case number one because there are actually three cases in determining RTH. Okay. Now we go to the second case in finding RTH. Now again, we go back to the circuit that we need to convert. Then we remove or disable all the independent sources. And what we do here is we apply an independent test source across the terminals. So we could either apply an independent voltage source or an independent current source. So let's say we apply an independent voltage source of 1 volt. Our objective here is now to find what is the resulting current after applying the test voltage. Okay. Um, Once we have determined the resulting current, so let's call it I sub test, we can compute RTH by using this formula. Of course, we could also apply a test current, an independent current source of 1 ampere. Uh, but the objective here now is to find what is the voltage across that test current. So let's call it V sub test. And once you get that, you could also compute RTH using this formula. Now, why do I apply 1 volt or 1 ampere? Well, that is the simplest test source that we can apply. Okay, we could apply 2 volts, 3 volts, or 1 ampere, 2 amperes. It really doesn't matter. You will still get the same RTH. So, well, solving, why do we have case 2? Because solving uh, RTH via case 2 is useful when we're dealing with dependent sources. So remember, when getting RTH, we don't disable dependent sources. And once we have that scenario, we cannot use case 1 in finding RTH. We need to use case 2. So let's apply our knowledge so far in this example. This example is the same as the one that we did using superposition. Again, we are asked to find the current through the 12 ohms, but this time using Thevenins theorem. So this is the solution. So now here we need to identify the part that we need to convert to Thevenins equivalent. So let's say I want to convert this part, so it has to be complicated enough. So this part here, I want it converted to Thevenins equivalent. So that means my terminals here are this one and this one. Okay, so say this is my A and this is my B terminal. Okay, so that means I want a circuit that looks like this. So the problem now becomes finding VTH and RTH. So how do we find VTH here? So again, we concentrate on the circuit that needs to be converted. We remove the part that is not part of the circuit that needs to be converted. So we remove the 12 ohms there. And we need to find the voltage VOC, where the positive uh, terminal is on terminal A. So, so to solve for VOC, um, we need to find the simplest loop that where we can write a KVL equation. So where it traverses also VOC. So that loop can be this loop. Okay. We could have used this loop, but this is not the simplest loop. And that loop must not contain any current source. Okay, so let's use the smaller loop. Now, in order to write equation there, we need to know the current that is flowing through these resistors. Okay, we need to find those currents, and let's assume those currents. Okay, so assuming those are the currents there, I have also identified the polarity of the voltage across those resistance based on the direction of the current. Take note that the direction of the current is arbitrary. You could have an opposite or different direction for the current. Now to yes, so once we determine these currents, we can then write the KVL equation from where we can find VOC. Now to get these branch currents, we can use mesh analysis by assuming these loop currents I sub A and I sub B. Okay, so once we get these loop currents, we can determine I sub 2 and I sub 3, for which we can get VOC. So how do we get these loop currents? Okay, so from the previous video that we have pertaining to mesh analysis, the equation in loop A, the loop that involves I sub A, is this one. So minus 12 by A. So So we add the resistance inside the loop. So 6 plus 3, we have 9 times the loop current inside that loop minus any voltage due to the loop outside. But take note that we don't have a loop current here because this is an open circuit. So therefore, there's nothing to subtract from this equation because this current is actually 0. So this is our equation for loop A. And from this equation, we could immediately get the value for I sub A. So this is our I sub A. Now for loop B, we notice that this loop contains a current source. So therefore, I sub B can be determined from that current source. That current is opposite to the direction that we have specified for I sub B. So therefore, I sub B is the negative of that current source. So now that we have I sub A and I sub B, we can compute for I sub 2. So I sub 2 has the same direction. So this is a branch current. It has the same direction as the loop currents. So the loop current direction is like this. And since it's the only loop current that passes through 3 ohms, because there's no loop current here, there's no loop current here. So therefore, I sub 2 becomes I sub A, and that is our I sub 2. Likewise, for I sub 3, the only loop current that passes through 5 ohms is I sub B, but I sub B is in the opposite direction that we have specified for the branch current I sub 3. So therefore, we have I sub 3 as the negative of I sub B, which we'll get there to be 2 amperes. So I sub 3 is really equal to the current source. Now that we have the branch currents I sub 2 and I sub 3, we can proceed to compute for V sub OC, which then becomes our VTH. Okay. Now for RTH, again, we go back to the circuit that we want to convert, but with the sources, independent sources disabled. So earlier, we have here a voltage source here and also a current source here. So we disable those sources. So here we disconnect, and here we apply a short circuit. So that's why the circuit becomes like that. Okay. And then from the open terminals, we compute for the resistance looking through the open terminals. So we notice that there are no dependent sources, so therefore we could apply case 1 in finding the resistance. So these two resistances are in parallel, and the combination is in series with this resistance. So this is our computation for RTH. So this one is the resistance for the two resistance in parallel plus the 5 ohms in series, we get 7 ohms. So therefore, our modified circuit becomes this one. And from here, we can compute our I sub naught by using Ohm's law. So voltage applied divided by the total resistance, we get our answer to be the same as the answer that we have using superposition. So that's it for this part one of Thevenins theorem. On the next part, we will have more examples.